Hello and good morning, or maybe good afternoon, ladies and gentlemen, and thanks for coming to this nice workshop, the first workshop on domination theory. I would like to thank the organizer of this workshop in Novosibirsk University in Russia, especially my friend Hamid. Okay, I would like to talk about total domination polynomial. Okay, sorry. As you know, dominating set is a subset of vertices of a graph such that every vertex which is not in the set must be adjacent to some vertices in the set. And the domination number is the minimum cardinality of a dominating set in a graph and is denoted by gamma of G. As you know, again, most of the papers before, I think, 2008 was about computing the domination number of a graph and finding some bounds, upper bound and lower bounds for domination number. And we have very nice books for in the domination number. But we do, nobody wrote anything about the number of dominating set of a graph. Okay. When I was the PhD student, I introduced the domination polynomial, such as this polynomial that you see here. dg and x is the summation of dgi xi. And dgi is the number of dominating set of cardinality I. So this is a generating function for the number of dominating set of a graph. Okay. So here we consider just how many dominating set with cardinality 5, 3, and so on. For example, easy example, you see here the domination polynomial of a star K1 and n is easily obtained by the formula x times x plus 1 to the n plus x to the n. After obtaining domination polynomial for past cycles and some specific graph, one of the main problems for us was obtaining general recursive formula for computing the domination polynomial of a graph. And we need some notation. As you see here, we denoted by G/U a graph obtained from G by removal of vertex U and addition of edges between any pair of non-adjacent neighborhoods of U. And this notation, G/U, is the graph obtained from G by removal of U and all edges incident to U. And also we need another definition for this notation. P sub U of G for any vertex U is the domination polynomial of G minus closed neighborhood of U such that vertices in the open neighborhood are dominating in G. Maybe this is easier that say that P sub U is polynomial that can't dominate instead of G minus U, which do not contain the vertex of open neighborhood. Okay, by this definition, we have this nice, I think, recursive formula for domination polynomial of a graph. I have a graph and a vertex U, then with this recursive formula, you can obtain domination polynomial of G, that you see here the graph G is, this polynomial is dependent to G minus U, and all of you know the removing a vertex, and this is a G by K slash U that I introduced before, and G minus a closed neighborhood of U, and here we have that polynomial P sub U that I introduced before. But let me to say that computing this polynomial is not very easy because of this P sub U, but with some condition, maybe P sub U be zero, okay? Be zero, so we have easier formula. Domination polynomial of graph products is a natural question in the domination theory, especially graph polynomials. And you see the domination polynomial of join of two graphs, and all of you know the join. If I have a graph G1 and here, for example, another graph G2, then if I connect any vertex in G1 to any vertex to G2, then I have a G1 VG2 or join of G1 and G2. And this formula is about the domination polynomial of join of two graphs. And as a consequence of this formula, for example, you see here the domination polynomial of a complete bipartite graph, since we can write the K sub M and N as the join of two empty graphs with n vertices and n vertices. And here you see the domination polynomial for corona product, and all of you know also know about the corona product because of corona disease, virus. For example, you see, let the G's graph be a graph G, and we have another graph, for example, H. G corona with H is obtained by putting the graph H for every vertex of G and connecting a vertex of G to all of vertices in H. Okay, for example, another H I put here and connect this vertex of G to all of vertices in the H. Okay, this is a corona of two graph G and H. And very interesting that the domination polynomial of G corona with H is not dependent to a structure of the graph G, and is equal to x times 1 plus x to the n plus domination polynomial of H to the n. N is the order of G. Okay. Another interesting theorem that Brouwer proved in the Tehran in a conference in 2009. I asked this question from Brouwer that I think that the domination polynomial of G at -1 is odd, and after 2 days he proved this nice theorem that for every graph G, DG, and 1 is odd. In other words, the number of all dominating set in any graph is an odd number. And we extend this theorem of Brouwer by for every odd number. In other words, the domination polynomial of G at R, where R is an odd integer, is always odd. So the domination polynomial, for example, in -1 is odd. So because in 2008, I thought at 7 maybe in 2007, I thought about the root of domination polynomial, and I had this guess that -1 can be a root, and so we could prove that the -1 cannot be a root of domination polynomial of a graph, because always is odd number. It cannot be 0. And so we have this conjecture in 2010 with my supervisor, Professor Peng, and actually, and my friend Woody, that if G is a graph and R is an integer root, then R is -2 and 0. And some papers have written about this conjecture, but the conjecture is open yet. Okay, let me to go to another subject in the domination polynomial, or maybe another graph polynomials. All of you know that if we have a two isomorphic graph, then their graph polynomials are the same, but the converse is not true. Okay, in other words, maybe we have a two non-isomorphic graph with the same domination polynomial. And so we can define the equivalence class over G as this bracket G, which contains the graph H, such that H is has a relation with G, and this relation is H is has a relation with G if domination polynomial of H is equal to domination polynomial of H. You know, for the first time, these equivalence classes for chromatic polynomial has studied well in the, I think, 2 or 3 decades before, and we have a very nice book in the equivalence classes of chromatic polynomial by some professor in Singapore and Malaysia. Okay, and we say that this graph is d-unique if the bracket of G is equal to this just G. And let me to say some example. For example, you know the generalized friendship graph that we noted by F sub n and Q is a collection of n cycle of order Q meeting at the common vertex. For Q3, we say this generalized friendship graph as friendship graph. You see here a figure that show generalized friendship graph. This one is F2n4, and this one is F3n4, and F4n4, and so on. And as I say, if we have a cycle of length 3, then this is a friendship graph that are important in the study of sum graph polynomial IT. And here another specific graph that denoted by B sub n and called n book of graph, constructed by bonding n copies of C4 along a common edge. For example, this is a common edge for this 3 C4, and here we have a one edge common for this 4 cycle C4. Every this C4 is a page of this book. Okay, so and you know that we can obtain this book graph by Cartesian product of some specific smaller graph. And it is nice that the complete of the book graph is not d-unique, and the domination polynomial of the complement of book graph and disjoint union of two complete graph of order n+1 have the same domination polynomial. So this complete of book graph is not unique. Okay, as another example, you see a theorem by me and Jason Brown in Canada, and Jahari, my former PhD student, that domination polynomial friendship graph you see obtained by this formula, and we could prove that the class of Fn, which is a friendship, is contained Fn and Bn slash V. And after 2 years, we could to characterize the class of D equivalent classes of friendship graph, as you see. You see is this exactly this set. You know, this for example, this is a graph G, and GOK1 is, as I said before, this graph. And now we consider GOK1 and join with another K1. For example, I should connect this vertex, new vertex, to all vertices of GOK1. Okay, and this kind of graph are in the class of friendship graph. And another example is about n-bar graph, which is denoted by bar sub n, and is 2n, has order 2n, and forming by two complete graph Kn and a single edge as a bridge. For example, you see here bar, I think the bar B4, yes, of order 8, and the bar, yes, bar sub 4. And you see the domination polynomial obtained of the B bar graph obtained by this formula, and so this graph is also not unique. Okay, let me to, after the domination polynomial, let me, it is obviously, since we have many dominating set, we could count the number of some kind dominating set of a graph, but most of them are not interesting, in my opinion, because we do not have many terms in the polynomial. But for some dominating set, it is, I think, is okay and is interesting to consider them as a new, for example, graph polynomial. As I know, I think after the general domination polynomial for general dominating set, we can consider total domination polynomial, and maybe independence and dominating set and independence domination polynomial is also interesting to consider. And some papers in this area have written by some authors in the journals. Okay, let me to introduce total domination polynomial. As I think all of you know, the total dominating set is a subset D of vertices such that every vertex in V is adjacent to some vertices of D, and total domination number denoted by gamma sub T is the minimum cardinality of total dominating in a graph. And similar to the domination polynomial, we have this total domination polynomial that denoted by capital D sub T, and is generating function for the number of total dominating set of G. And you see here the coefficient of x to the I is the number of the total dominating set of a graph with cardinality I. For example, you see here the total domination polynomial of N, which is a complete graph with order n. And note that if we have a graph with isolated vertices, then the total domination polynomial of a graph is 0. So we consider a connected graph here with isolated vertices. Macrostat in 2014 obtained a recursive formula similar to domination, which is dependent to G minus U, Gs slash U, and G minus the neighborhood of U and the neighborhood of U, and we have also here a polynomial P sub U, which is a polynomial the same to general domination polynomial, and this polynomial that contain the total dominants of G minus U, which do not contain any vertex of the neighborhood of U. And you see here, if we have this condition that the closed neighborhood of U equal to the closed neighborhood of V for EUV, then this for this P sub U should be 0, and we have this easier recurrence formula for computing total domination polynomial. Okay, as a corollary that obtain this total domination polynomial for paths, as you hear, we have a recurrence relation with two variables, and the order is 4, because here is and we need to look at the graph Pn minus 1, Pn minus 3, and Pn minus 4 with this initial condition. And you see, again, similar to domination polynomial, we had considered the total domination polynomial of join of two graphs, and we have the same formula for join of two graphs. And as an example, if we consider Wn as the graph K1 joined with C and minus 1, then we have this total domination polynomial for real of order A. And as another theorem, you see here total domination polynomial for some specific graph, as I introduced before. This is a friendship graph, and we have this polynomial for total domination polynomial friendship, and here this is a generalized friendship graph Fn and 4. And I think we have some formula for Fn and K greater than or equal 4, but I didn't write here. And for another specific graph, book graph, you see a polynomial total domination polynomial of book here. And again, we consider some another product and obtain this formula for total domination polynomial of K1 and H. Here we have just K1, and I have a graph H, and I connect just where this K1 to any vertex with H, and we have this formula. And I think I cannot remember that. I think we couldn't to generalize this formula for any two graphs G and H, and maybe this is remain as open problem. I think that what is a total domination polynomial of two graph G and H. And another theorem that you see here that I think is not bad, a theorem that says there is no connected graph that dg and x is equal to d sub t of g and x. And there is no graph that its domination polynomial be the same of its total domination polynomial. And I think this is Okay. A root of this polynomial, we call the root of domination polynomial domination root, and we call the root of total domination polynomial as total domination root. And there are some papers on their domination root and some papers on total domination roots. And we denote by the set of all roots of total domination polynomial of G by this notation Z and D sub T and G and X. And we have this theorem that if G is a graph of order n with minimum degree delta, then all roots of this polynomial are in the circle with center -1 and 0. So we have a circle with this center, and a radius of this circle is dependent to order of graph and minimum degree of graph, and the radius of this circle is delta roots of to the n-1. In other words, if Z be a root of domination root of graph G, then we have this inequality for Z. And let G be a graph of order n, and if the minimum degree of graph is greater than equal to 2n over 3, then every integer root of the total domination lies in this set -3, -2, -1, and 0. So -4 and -5, -6, and so on cannot be roots, integer roots of total domination polynomial. Yeah. You remember about the domination polynomial that we have just we have this conjecture that there is just two integer root for domination polynomial, -2 and 0. And here we have this conjecture that if G is a graph and R is an integer root, then R should be -3, -2, -1, and 0. I think this is a good conjecture, but we could do, as you see here, as proof for any graph with this condition that delta greater than or equal to n over 2. Okay, and but by this conjecture, we have another question in mind, and problem that is it possible that we have a graph with just two total domination roots? And the answer is yes. If you the graph and the subset, the set of roots of total domination polynomial is -1 and 0, then we can say G has at least two support vertices. Okay. But until now, we couldn't to characterize any graph with this condition that graphs with total domination roots -1 and 0. Okay, this is, I think, good question to study for PhD student, for example, a researcher. Okay, and we have also this theorem that if G is a connected graph, and if all roots of this graph are real, then the minimum degree is 1 or 2. And so if delta, we have this corollary that if delta greater than or equal to 3, then we have some complex roots. And the second one says that the polynomial, total domination polynomial, has at least this number non-real roots, delta -2, non-real roots. And Mr. Okay. I think Mr. RD and the speaker is open. Here we have another theorem about characterization of graphs with two total domination root, and these two are -3 and 0. If G is a graph of order n with minimum degree at least 2, then -3 and 0 are all the roots of domination polynomial of G if and only if G is C3 or C6. So this one is characterized by this theorem. And we have another theorem about, again, roots that says that if G is a graph with delta greater than or equal 3, and if this polynomial has exactly 3 distinct roots, then this set Z, D, T, G, and X is a subset of 0, and this complex number -2 plus minus square root of 2i and -3 plus minus square root of 3i over 2. I think this is interesting that I think these two numbers, actually 4 numbers, are roots again for the ordinary, the general domination polynomial again. If I say true, yes, I think I am true. Okay, we have this actually. Let me to say that it is very interesting that the roots of any graph polynomial, the set of roots of all domination polynomial of all graphs are dense in the plan. Okay, so we think that this is true also for total domination polynomial. To tack to this conjecture, we have this theorem that says that the total domination polynomial of friendship graph f sub n has a real root, as you see in the figure, in this interval minus n and minus natural logarithm ln n for n sufficiently large. As you see, we have a roots in the when n go to infinity, we have any roots in the left of the x-axis. And also we have the same result for generalized friendship graph f and 4, and this polynomial has a real roots in the, again, this interval for n sufficiently large. But as I told before, I think we couldn't to finalize this conjecture that the set of roots of all total domination polynomial are dense in the plan. You know that we have this theorem again for chromatic polynomial that so-called from New York University proved it, I think, more than 25 years ago, I think. Okay, let me to define irrelevant age. We say an age of a graph is irrelevant age if when we remove the age, the domination polynomial doesn't change. Okay, so total domination of G is equal to total domination of G minus C. And this is, I think, good definition, but finding this h in the polynomial, I think is not so easy problem. And we need this definition that if the graph and a vertex V is a total domination cover, if each total dominating set of G minus U, G minus V contains at least one vertex of neighborhood of U. And we could to prove that if UV is an irrelevant H in G, then two vertices U and V are total domination covered in G minus E. So necessary condition for irrelevant H of for the total domination polynomial is this theorem. But the converse is not always true. And you see here in the following, this graph, the vertices U and V are total domination covered in G minus U, while E is not irrelevant H, because if you compute the total domination polynomial of G is this polynomial, but you see the total domination polynomial of G minus E is not equal to this polynomial of G. So the converse of this theorem is not true. And if there is a graph with A's UV such that the closed neighborhood of U equal to the closed neighborhood of V, and if there is a support vertex in closed neighborhood of U, then is an irrelevant H. I think this is a good theorem to characterize and study DT equivalence classes for total domination polynomial. And another theorem says if G is a graph and EUV is an H, and if U and V are adjacent to support vertices, then E is an irrelevant H. And also another theorem about irrelevant H that says that if there is a graph with this H such that the closed neighborhood of U equal to closed neighborhood of V, and if there is a vertex W in the closed neighborhood of U such that the neighborhood, open neighborhood of W is subset of neighborhood of U, then is irrelevant H. As an example, let to consider this graph that I think this is a very important graph in the total domination theory. We have a graph H, and we consider n copies of P3 that identify with any vertices in H, and we denote this graph by H parentheses 3. And because these, by previous theorems, we could prove that these edges are irrelevant edges, so we can conclude that domination polynomial of this graph H3 and X is equal to domination polynomial of, when we remove these edges from H, then we have P3 NP3 and X. So these two polynomials are the same, and we know that this is the product of domination polynomial of P3, and this is equal to domination polynomial of P3 to the n. Domination polynomial of P3 to the n, and it is easy to see that the polynomial of P3 is x times x plus 2. Okay, so we have this theorem for total domination polynomial of H3 using irrelevant H's. As another result and consequence, consider this specific graph lollipop, which denoted by L, M, and N, and obtained by a graph K, M, and a path on N vertices that we join a leaf of Pn. This graph is a Pn, and we connect these end vertices of Pn to a vertex of Kn. So we have this lollipop, and again with using the irrelevant age, we can obtain this formula for L, M, and 1, and sorry. Okay, and similar to another graph polynomials, we can have equivalence classes for total domination polynomial. As I said before, a class of G is the set of all graphs which are dt equivalent to a G, and we denote this equivalent this relation by tilde sub t, and means that if we have this notation, then total domination polynomial of G is the same of the total domination polynomial of H. And we have, we say total, a graph is a unique, total dominating unique if the class contains just graph itself. For example, here you see all the dt equivalent classes of connected graphs of order 4. And here you see another graphs of order 4. They are in the one class, and you see these two are in one class, and so on. And you see here of order 6. There are all these graphs in the first row are in the one class, and you see their total domination polynomial in the below of their figures. And another figures that we could to characterize their classes. And we have for the classifying the classes of dt equivalence classes, we need this nice theorem that says that if we have a graph G of order n and degree of vertex V is n-1, then G is dt unique if and only if G minus V is dt unique. It is a good, I think, an easier theorem that can help us for classifying the equivalence classes. For example, it is easy to see that the complete graph is dt unique and friendship graph is dt unique, but you saw that Fn is not dt unique. D unique is not the domination polynomial of a friendship graph is not unique, but total domination polynomial of friendship is unique. And you see another theorem about the class of S star. You see here in this class we have lollipop graph L1, Ln1 minus E, and so on. So the total domination polynomial of a star graph is not unique. And another graph that we I think it is has a very easy definition that we have a graph G, and we join M sub I new vertices to each vertices Vi from the vertex A. And by this theorem, we could present many graphs in the form G corona with empty graph with empty graph of order M and so on, which are not DT unique. Okay, so this family contain many graphs that are not DT unique. And also you see here that the class of G with Km overline contains the sun-like graph with itself. Okay, another that I think this is a last section. I think is about of polynomial and unimodality of total domination polynomial of a graph. All of you, maybe you know about the unimodal. We say if a sequence A0, A1, AN is unimodal if there is some K called mode such that we have these inequality that we have A0 less than or equal A1 until AK minus 1, AK, and then after the this index K, we have inverse relation. AK is greater than or equal AK plus 1, and so on. And we say a polynomial is unimodal if the sequence of its coefficients is unimodal. And it is log concave if we have this relation for the coefficient. And also we say it's symmetric if AK is equal to A sub n minus K. And you know, a log concave sequence of positive number is unimodal. And another definition that you see here, maybe you have seen this conjecture from 2009 that we think that the domination polynomial of a graph is unimodal, and I think more than 10 papers have written by very good researchers in this conjecture, and I think the conjecture will be solved soon, and many nice results about this unimodality published in the journal. And we have also the same conjecture for total domination polynomial that says the total domination polynomial of a graph is unimodal, and similar to general domination polynomial, that this inequality for D is true. We have again this inequality for the number of total domination polynomial of G. So for every I between 0 and half n, we have this inequality, but we do not. We know actually in 2017, I think, or before, we couldn't find anything about I greater than or equal n over 2. And we have some specific graph here as called firecracker. You see here, and the below one is generalized firecracker denoted by K1 and K. And yes, you see here this the second figure is F5. Polynomial of this kind of graph, and for example, this kind of graph have unimodal total domination polynomial. graphs that have a unimodal total domination polynomial are can see in this theorem. And okay. And also we could prove that the total domination polynomial of book graph is unimodal, and also for general friendship, I think is we could to prove is unimodal. And recently we have some similar result from, I think, Brown and his team in the Canada, that if R sub k is greater this number, then we have this inequality. And if the minimum degree is greater than this number, then this polynomial is unimodal with at most with mode ceiling and hour 2. And if this is a regular graph, M regular with 2 n vertices and m greater than n minus 1, then the unimodality of total domination can be proved. And as a corollary that you see here, the total domination polynomial of a complete graph with K2 is also unimodal. Okay, there are many problems, open problems and conjecture in the total domination polynomial that I have written here, and I think I said before, and you can think about them. Thank you for your attention, and thank you again, Hamid and organizer, to inviting me to be a speaker here. Thank you so much.
Professor Alikhani, thank you very much for your nice presentation. That was really great, and we really enjoyed it. Dear all, please thank a speaker. And thank you. And if you have any questions, please share with us. We would be happy to listen your questions. Please turn on your mic if you have any questions. Okay, it seems that there is no question, and let me again thank you, Professor Alikhani. And right now, I'm kindly asked to manage the workshop as a chair, and it would be great if you could help us on this matter.
Okay. Okay, Hamid, thank you so much. I think I had many
participants.
Yes, I told many results here, and maybe there is no question. Maybe it's a good time to have because we have
take a photo. Yes.
Yes, take a photo. If participant turn on webcam.
Dear all, please turn on your webcams to take a photo for a memorial. Sophia, can you hear me?
I see Elena. How are you, Elena?
Hi, Elena. Hi, Ismail. Nice to meet you.
Oh, yeah, nice to meet you. Yeah, it was great talk. Yes, thank you so much.
Okay, thank you, Elena.